This is AQA A-Level Chemistry. We are on the Alkanes topic from year 12, and this is video number 2 in this series for the topic. In this one, we're going to take a look at fractional distillation and cracking. So as always, I'm going to recommend that you try each activity, pausing as you go, and then you can check what your own level of confidence, knowledge, and understanding is. So let's take a look. First of all, we've got a table of information here. What is the trend in boiling point as chain length increases? And using your knowledge from the bonding topic and from GCSE, why do we think that's the case? So the first thing to say is that the chain length increasing leads to an increase in boiling point. Why is that the case? Well, from the bonding topic, we learnt about intermolecular forces. It means that in bigger molecules, there will be stronger van der Waals forces. And if there are more stronger van der Waals forces, more energy is needed to overcome them, so the boiling point will be higher. And it's that principle that actually helps us to understand how fractional distillation takes place. So now let's have a think about this. We've got a student who has said that a fraction contains a particular chain length with a specific boiling point. Why are they wrong? And again, I can go back to this table so we can see it. We actually don't have a single hydrocarbon. We have a range of hydrocarbons. Petrol could be between 5 and 10 carbons long. So a fraction is a mixture of hydrocarbons. That means they won't all have the same chain length, but they will have similar chain lengths, and because they have similar chain lengths, they will have similar boiling points. There's also some information here about crude oil. It's important that we remember that it's formed over millions of years under the ground in the absence of oxygen, and it comes from plant and animal remains. Because it takes so long, it is non-renewable. When it's gone, it's gone. Okay, let's go on and take a look at fractional distillation, and we've got some questions here. And so the first one, where is the hottest part of the column? Well, this diagram actually shows us the hottest is at the bottom, 350. It's only 25 at the top, but it also makes sense that we are heating the crude oil and we have a furnace down at the bottom. And will longer chains condense near the top or the bottom, and why? And if we take a look at this, they are going to condense at the bottom. We can see that fuel oil is down here, whereas refinery gases go all the way to the top. And that's because they have higher boiling points, so they condense at higher temperatures, whereas shorter chains are able to rise up much further before they condense. So I'm going to summarize some of the key ideas. If you can remember the 4 key points about fractional distillation, you will be able to develop a good answer within the exam. So my start point is always to remember that we take the crude oil, we evaporate it, and then we condense it. That's absolutely fundamental to what we're looking at. Now from there, we know that the column is hotter at the bottom and we know it's cooler at the top. So we know that the condensing will happen at different points in the column, dependent on boiling point, which is dependent on chain length. So that takes us to the end of the fractional distillation, and let's now take a look at cracking. So we need to think about why we crack crude oil. And I'm going to put the table back up for you to think about it. And you can take a look, I think particularly at the percentage present data. And once you've taken a look at that, we go back to the question, and why do we crack crude oil? And it is purely down to supply and demand. If you take a look, only 8% of this crude oil sample is petrol, but we know how important petrol is to so many millions of people's lives around the world. So supply does not meet demand for those shorter chains. But furthermore, we have a greater supply than is needed for the longer chains. So cracking involves taking those long chains, breaking them down into 2 or 3 pieces, and that gives us a greater supply of the shorter chains that we have a much greater need for. Now, one key fact about cracking is that we will end up making alkenes. And we're going to talk about that in a different topic, the importance of them. But here, just a quick question. Can you remember what the functional group of an alkene is? And hopefully you can remember that it's the C-C double bond. It's something that you're probably already very familiar with and will become much more familiar with. So this table is absolutely vital that you remember every fact that we're about to fill in. So it's a good opportunity for you to see what you can remember. So pause it, see what you can do, and then we'll review. Now I'm going to go to the most obvious one. Catalytic cracking has a catalyst, thermal cracking does not have a catalyst, so I'll get rid of that there. In terms of the temperature and the pressure, you have got to remember the catalytic cracking, it's a high temperature and a slightly raised pressure. You also need to remember that the catalyst that we use is zeolite. Now, if I go to the other side, we've already got a high temperature for catalytic cracking. It's actually the same answer for thermal. They're both done at high temperature. The key difference is actually in the pressure, that we use a high pressure for thermal cracking. So we would use different types of cracking depending on the product that we wanted, because thermal cracking is far more likely to give a higher percentage of alkenes, and that's really important for polymerization and plastics. Whereas if we wanted motor fuels or aromatic compounds, we're far more likely to use catalytic cracking. Aromatics, for context, is benzene-related chemistry, and we learn much more about those in year 13. Okay, that takes us to the end of this section. One of the things that might come up in cracking is writing equations to show the breakdown of a long compound into shorter molecules. It's always important that you read those questions carefully, have a look at past paper questions, and there are some video examples of those that you can find in the Alkanes playlist where you can get some experience with them. Okay, thank you for listening. Goodbye.